Well, welcome everyone. Great that you're here on 9 a.m. in the morning. Welcome to the talk Predicting Article Demand with Temporal Fusion Transformers. So my name is Sharon Gieske and I'm the tech lead of the data science team at Picnic, fastest growing online supermarket in Europe. Our team is a centralized data science team that builds end-to-end machine learning solutions for the whole business. So we do field projects in fields like personalization, finance, and of course demand forecasting. And I'm incredibly excited to tell you more today about how we're using the Temporal Fusion Transformer, so a state-of-the-art deep learning model at Picnic for demand forecasting. Is it clicking? This should be good. OK, so let's start with this statement. Demand forecasts are critical for retail. So any company, any retail company that wants to grow needs to have demand forecasts because they feed into so many critical operational processes. You need to be able to estimate what people are going to order, when they're going to order, how much they're going to order to make sure that you have enough inventory, you have enough people, and that you do your marketing and promotions right. So this is incredibly important, and for Picnic, demand forecasts, and specifically article demand forecasts, are essential. So let me give a very quick introduction about Picnic before we dive into the cool modeling stuff. So maybe show of hands here, who has heard about Picnic? OK, that's good. Who has heard about Picnic before the conference? OK, it's getting better. So after this talk, everyone can raise their hand, of course. So Picnic is Europe's fastest growing online supermarket. We operate in 3 countries, the Netherlands, Germany, and France, and of course have plans to take on the world. And our mission is simple. We want to make grocery shopping simple, fun, and affordable for everyone. So how do we do this? We're mobile only, so we got rid of all the physical stores. You can order with us until 1 day in advance. And we deliver your groceries to your doorstep in fixed time windows for the lowest prices. So because we are a grocery store, we have some additional challenges for article demand forecasting that you will find less at non-food retailers. So the first challenge is that we sell perishable products. So we have fruits, vegetables. They have an incredibly short shelf life. And this means that if we over-forecast, we risk a lot of waste, which is a lot of loss of revenue. The second challenge we have is that because of these perishable products, we operate as a just-in-time supply chain, which means we order as late as possible to get the products as short as possible on the shelves, to get them to the customers as fresh as possible. But this also means that we have very little margin for error. And the third challenge is that we're mobile only, which means that if we under-forecast and we have unavailability, this will hit us enormously. This has a huge impact. If a customer tries to order their groceries with us and there's only one product of maybe the 50 products they want to order and it's not available, there's a high probability that people will actually abandon their basket completely because they have to go to the physical store anyway. So these 3 additional challenges make it super important for Picnic to have very accurate demand forecasts, article demand forecasts. And this is also why we invested in machine learning to do these forecasts. So let me sketch a bit of the landscape or the data we have and the requirements we have for machine learning models. What models we already tried before we went into this Temporal Fusion Transformer model. So let's say we want to predict how many apples people are going to buy tomorrow. So we want to predict for 1 day in advance. And a very typical data point that you can use here is previous demand. So previous demand is a very good indicator of future demand. And this is a time series data point or data points that has some trends over time. Now, often we don't only want to predict for 1 day in advance, but we want to predict for 2 days in advance, 3 days, 7 days. So multiple days, multiple steps into the future. And this is called multi-horizon forecasting. Next to this, next to the temporal previous demand, we also want to use other temporal data points. For example, weather is a very good indicator of demand. You can imagine that in a heat wave, people will stock up on ice cream or buy ice cream more. And this is something that is very interesting to put into your model. So we really want to add that as well. And we have this in the past. We might have some forecasts in the future. Not sure how accurate they always are, but we have that. Now, next to these time series and these temporal data structures, we also want to have another type of feature inputted in the model. These are features that we know in the past, but also in the future. And a good example here is the day of the week, or if a holiday is coming up. So this has quite some impact on how people are doing their grocery shopping. For example, think of the groceries you do before Christmas or before Easter. And these are things we also know in the future. Now, the third type of data point is features that we know in the past, we know in the future, but are static throughout the whole period. A great example here is the category. So in this case, it's the category fruit, but it can also be for what kind of store we're predicting for what kind of city we're predicting for, and this is something that is static throughout the time. Now, this is a bit of the data and the requirements we have for our model. So what did we do at Picnic? Well, we started with a non-machine learning solution, which is a pretty good, solid baseline. So we started with the moving average, which is just the average of the last week, of the last 2 weeks. And this worked pretty well in the beginning. But as you can imagine, this doesn't include all the other types of features where we know it has some impact, like weather or holidays. So we quickly realized that we wanted to do something more. We wanted to get them more accurate. And this is where we decided to go for gradient boosting trees. Gradient boosting trees are pretty good. It had solid performance, and they served us well for a long time. You can input all types of features. This is something many companies use. You find it on many Kaggle competitions. So it's a pretty good model. But it had one big downside or disadvantage that we figured out during COVID. So the disadvantage of these models is that it cannot extrapolate to values it has not seen before during training. And during training, or during COVID, customer behavior radically changed. People were stocking up on toilet paper, hand sanitizer. This is something that our model hadn't seen before, and our model actually couldn't pick up. And this is where we decided we needed something more. We needed another model that could help us improve our forecasts. And this is where the Temporal Fusion Transformer came in. And this is what we've been using now since over a year. So the Temporal Fusion Transformer is a deep learning model, a deep neural network that is specifically suited for time series forecasting. It originated out of the paper published in 2019, so pretty recent, from a collaboration of the Oxford University and Google. Now, because Temporal Fusion Transformer is quite a mouthful, you might hear me call it TFT sometimes, so then you know it's the same. So what makes this model so special? I want to highlight 3 characteristics. There are many more, but I think these are the 3 most important, before we dive into the technical architecture. So the first important characteristic is that it is adaptable to different feature types. So we talked about these feature types before. The Temporal Fusion Transformer is really good in temporal patterns, where a gradient boosting decision tree has tabular data as input. It doesn't know the temporal patterns between those different columns, so you really have to feature engineer that in. The Temporal Fusion Transformer has that out of the box. Next to that, if you compare it to conventional deep neural networks, they often can only handle one type of feature. So either you have only things that are known in the past, or everything needs to be known in the past and the future. And often it cannot process these static features that are just one-dimensional that needs to be passed throughout the model. The Temporal Fusion Transformer can handle all those things. The next interesting characteristic is that it is multi-horizon. So it can forecast multiple horizons at the same time. If we would create these models with gradient boosting decision trees or regression trees, you would often create a model for 1 day ahead, then another model for 2 days ahead, then 7 models for the next week. And often you want to add the input of a previous model into the next model, which gives a lot of risk for error propagation. Now with this model, you can have 7 models or 7 predictions at the same time, or multiple predictions actually. So this is a very strong feature of the Temporal Fusion Transformer. Now the third characteristic, which is I think the coolest, is that it has explainability out of the box. So if you compare, you might have heard about SHAP and LIME methods that are more traditional. They work pretty well for traditional models, but they're not so good for time series. They cannot really show the temporal explainability. And if you look at more conventional deep neural networks, usually they are pretty black box. It's pretty difficult to explain why a specific prediction came out of a deep neural network. This model has specific features, which we'll dive into further in the talk, that actually bring this explainability, which makes it an incredibly powerful model. So how does it do this? I hope you had your coffee. We're going to go technical. I'm going to show you the model architecture, and we're going to walk through it step by step, because it has specific components that add to these different characteristics that we've talked about. So for the next image, don't get overwhelmed. I don't expect you to completely understand it. We're going to walk through it together. So this is it. This is a pretty complex beast, but it consists of easier components that all add to these special characteristics. So to make sure that this fits on my screen, we're going to make it a little bit smaller. So I'm going to show it like this. What is important here to know is that on the left side, the static information comes in. In the center, the past features come in, so like the past demand. And on the right side, the future features come in, which were the day of the week, the category, etc. So this is important for the structure. So let's dive in. The Temporal Fusion Transformer. The first step is that it uses variable selection to find out what features are important. So this is the very first step at the bottom. And you see 3 different boxes, which is it does variable selection for static features only, for past features only, for future features only. So they are separate. Now, how does this work? We'll zoom in a little bit. This is what goes on behind the scenes. And this step of variable selection will make the model more robust. And the most important part here is actually the sum that you see on top. So what you see is the multiplication of a feature embedding, which is the E thingy. I forgot the name of that. The feature embedding times its weight, which means because we do this for each feature, we can actually, or the model can learn to set weights to 0, silencing those features. It can silence noisy features. It can silence features that actually hurt the loss of the model. And it can do this by itself. So where deep neural networks often can overfit on unnecessary features, this model is so robust that it can handle this by itself and silence those features, which is a pretty cool feature. Now we know what features are most important. Let's go to the next step, which is where we encode the static information throughout the model. So this was the category or the city we are predicting for. So because this is often a different dimension than the temporal data, because it just has one value, we encode it first, transform it to a specific dimension, and then we just feed it through every step of the model. And this is how the model can also learn that there are different patterns for fruit compared to vegetables. So this is a very strong feature to add this static information throughout the model, which was not really possible or not easily possible with other deep learning models. Then in the third step, this is where we learn temporal context with LSTMs. So here we learn more about the history and we can process the time series to get to our future demand. This part learns short-term temporal patterns, and it produces context-aware embeddings. So let's say we're today at T0. At T, we want to add some information of what we saw the day before, and then the day before as well. So this is what the LSTM does here. And the past inputs go into the encoder. The future inputs go into the decoder. And this is how we learn short-term temporal patterns in our time series forecasting. Then the fourth step is what puts transformer into the name Temporal Fusion Transformer. This is where attention comes in. And this is where we learn long-range dependencies through attention. So where LSTMs were good in the shorter-term dependencies, the shorter-term patterns, it gets worse over time. The longer your pattern is, the more difficult the LSTM can pick this up. But the attention layers can actually pick this up because it has links to every time step in your time series. It learns what time steps to pay attention to, and it can also provide explainability. So how does it do this? It actually shares the weights for the attention layer. So there's only one set or matrix of weights that we can plot. So this is actually a plot from our own models. On the x-axis, you see the time index, so the time steps in the past. On the y-axis, you see the amount of attention the model puts on it. And you see these peaks at 7 days ago, 14 days ago, 21 days ago, which is the weekly shopping pattern people have. So this makes a lot of sense if you think about grocery shopping. And this really helps us to also explain to the business, these are the time series that the model pays attention to, or the time steps. Now, the last step of this model is where we create quantile forecasts. So instead of just predicting one point, only one value, we predict for multiple quantiles, which can help us create prediction intervals that we can use to communicate how certain our model is. So the model trains with a specific type of loss, which is called the quantile loss. And it can predict for the 10th quantile, the 50th quantile, 19th quantile. And we can take two of these quantiles and then create a prediction interval from that, signaling the model uncertainty. So this is it. If there's one picture you want to take today from a slide, this is the slide. So let's recap before we continue. The Temporal Fusion Transformer first figures out what features are important per type. Then it encodes static information throughout the whole model. It learns temporal context, short-term temporal patterns with LSTMs. It learns longer range dependencies with the attention layer. And then it uses quantile forecasts to get prediction intervals. So it's a pretty cool model. I hope you're still with me after this technical, in-depth conversation. Now, such a model, of course, doesn't come without technical challenges. And I really want to share those with you today as well. So the first technical challenge that we face is that it has a steep learning curve. It is a more complex neural network. I hope that after this talk, the learning curve will be a bit less steep for all of you. But of course, it's more difficult to understand, and especially a model that is so ingrained with all the operational critical tasks that you have at your company. It's important to take the time to understand such a model. So it has a steep learning curve, and it will take a bit more time to understand it. Now, the second challenge is that with deep neural networks comes the request for deeper hardware. So this is not something you can do on a CPU. Where the gradient boosting trees we could train on CPUs, even train locally, the Temporal Fusion Transformer needs a GPU. And even then, training the model takes several hours. We are actually training the model on a GPU and then doing inference on a CPU. So that is possible. Would not completely recommend it. If you can get GPUs for both, I would do that. But this gives an additional challenge, and it also gives additional costs. So you need to make sure that it's worth it. And the third challenge is that there's less documentation. So with such a state-of-the-art model, people are just using it less. So there's less documentation to be found. We are using the open source package PyTorch forecasting, which is pretty well documented. But if you have an issue or a question, probability is pretty low that you will find it on Stack Overflow. So make sure you add some additional time for your developers to really build on the model. So these are the challenges we definitely faced during the implementation. Now, if there's one thing I would like you to take away from today, it's to actually not start with a TFT. So with any good machine learning approach, you have to have a solid baseline. And if your baseline is a linear regression, it covers 90% of your forecast, this is not going to be worth it. But if you're at a stage where Picnic was, where you really need those additional accuracies, and you can handle those technical challenges, this model can definitely be worth it. So what did it bring Picnic? We've been using this for over a year in production, and the contribution is threefold. So first, we saw 20% increase in our forecast prediction, which is huge. We specifically saw an increase in the slow movers, so the products that we don't sell that often, which is pretty difficult to predict. So we're incredibly happy with that, of course. But then also we saw that we could have more explainability. We could use all these plots to communicate with the business, but they can also feed into the model development, having data scientists more focused on where we can add more value to the model. The third contribution is that with the prediction intervals, we can create safety margins, or we can adjust our safety margins based on how certain a model is. And with that, we can balance waste and unavailability. So we are pretty happy with this model. Now that already brings me to the key takeaways of today. So we talked about that demand forecasts are critical for any retail company, and it can be very interesting to invest in machine learning for demand forecasts. We talked about the Temporal Fusion Transformer, a high-performing deep learning model that is both versatile because it can handle all these different types of features, and it has explainability out of the box. But it does come with steep learning curves and hardware requirements. So don't start with a TFT, but when you're ready, it's going to be worth it. And it was worth it for Picnic. And with that, I'll take questions.
Thank you, Sharon. So are there any questions? There's lots of questions. Maybe just come here to the front quick. If you're standing at the back, there's a couple of seats at the front if you want to sit, if you want to save your back, your eyes.
You talked about quantiles. Was it like confidence intervals, or what are they about?
Yeah, so with the quantiles, let's say you find this slide. Let's say you predict for the 90th quantile, which means that the model learns to create predictions that for 90% of the time fall below that. Yeah.
Confidence interval.
Yeah. So you can. So this is pretty cool. So this is how you can interact it with your safety margins.
Thanks for the talk. So I would like to ask, before you jump from the boosted trees to this model, have you tried something in between, like just simple LSTM or these other simpler transformer blocks? Have you tried it?
So the moment we started looking for the next model, we actually tried, I think there were 3 different models. We tried an LSTM, a CNN, and a TFT. And we actually saw that the TFT was performing best, so we continued with that avenue.
Thanks.
Hi, yes, great talk. I was just wondering on the model resolution, maybe 2 questions, but the one is, was this good at picking up sparse data or intermittent, like where the sales are 0 and 1 per day? Because that's sometimes quite a big problem I've seen. And then the other one was, did you throw all the data and then there was like a category for fruit versus this, or did you break it up into different models for each article, basically?
Yeah, so we use one model for them all. So before, when we tried the gradient boosting trees, we were planning to create a model for fast movers and slow movers separately, and maybe some additional models. This does it all in one, which is really nice for maintenance. So that really helps. Your other question was about sparse data, right?
Yeah.
So there are some of the products that we don't yet predict for. So the extreme slow movers, where we have a very volatile demand, where maybe someone buys it once a month, or maybe a handful of people, and it's still difficult because there's no data. So this model still needs data, right? It's not a magic thing that just can predict. So here we try to use more moving average. We try to use reference articles where you say, oh, this article looks like something else. So there are some additional business logic rules on top of this.